Okay, so just collected the take-home quiz. Today it's really kind of exciting. We've been finding area between curves. You know, we added up an infinite number of infinitely thin rectangles and we found the area of a region. Today we're going to find the volume of a solid. Volume. But kind of like with the same idea, you know, the idea that you can sum up with a definite integral, an infinite number. In this case, today we're going to be using disks. So before we can actually get going, we need to figure out what would the volume of a single, we call it a disk, and really it's a right circular cylinder. It's just a cylinder. And so I wanted to see first, instead of just giving you the formula, I bet some of you remember how to get the volume of a cylinder, right? If you know the area of the base, you multiply it by the height, you'll have the volume. Any prism's going to be like that? I don't think some people. Well, what's the area of the base? Pi r squared. Now, okay, and what is the height the way I've labeled it this way? dy. You do know. So the volume of a cylinder with a height of just a small change in y would be pi r squared dy. Now I could also take the cylinder, or disk, we're going to call them, turn it on its side. Right? So now the height would be a small change in x. Could you tell me what the volume of that disk would be? Yep. Pi r squared times, now the height is dx. Is it okay? Or you don't get it? I guess? Yeah, I know. When people say stuff in the room, no one hears. Well, what is the area of a circle? Yeah. So the area of a circle is pi r squared, and then when you multiply it by the height, you get the volume. There's no 2 in there. Now, you're thinking of 2 pi r for the circumference. You got the 2 in there. Okay. All right, well, today we're going to be finding volumes of solids. I used to have really cool applets so you can kind of visualize, but you're going to have to rely on my drawing today. There she is. Big tray of French fries. Okay. I'm going past it. I am going to show you what I was able to find. It's not perfect. I have a few little applets. Let me just minimize this for a second. So here's the idea. And I don't know how to make this larger, so I'm sorry about that. But we're going to start with a curve. We're actually going to start with an enclosed region. So let's say we start, pause this real fast. Okay, we're going to start with an enclosed region. You see that? That's two-dimensional, no volume. But what we're going to do is we're going to revolve it about the x or the y-axis to create a solid. That's why these solids are called solids of revolution. Now watch what happens. It's very slow, so when it starts evolving about, in this case, it'll be like the x-axis. You see how now all of a sudden we have a three-dimensional object? Oh. And if you ever been to a party where they have those decorations, it looks like cardboard, and then you open it up, and you have like this, yeah, that's what this is like. So we're going to find the volume of a solid that's created by revolving a region, area, about an axis. And you can even think of it as one slice at a time. Each little slice, if you revolve that thin little rectangle, that one slice is going to be a disk. Now, once it finishes going around. And the way we're going to come up with the volume of the whole solid, get ready, it's almost going to happen, is we're going to integrate, we're going to add them up, and we'll have the volume of the whole solid. Oh. So if you did that for every single one, all right, it's not the best, but it's all right. It's pretty good. I had another one to help you kind of see it. Where's my other one? This isn't really good because you don't see it revolving around, but if you took a region, you revolved it around, every slice would be a circle. And it doesn't matter where you think of the slice. You're going to have big circles and smaller circles, right? Or really disc, I should say, because they've got dimensions. But then the idea is if you added all of the volumes of all these discs up, you'll have the volume of the whole solid, right? So that's what we're going to do. We're going to find volumes of solids of revolution. Crazy. There. Okay. I don't know. Oh, I'll wait till I get to. Oh, that was the area stuff. So yeah, if we know that the volume of a single disk is either pi r squared, I forgot which one I had first. One of them was pi r squared dy, and the other one was pi r squared dx. If you want to add them up, you can do it by integrating. So you can just integrate, and you'll get the volume of the whole solid. If the thickness of each slice is a small change in x, we'll integrate from the smallest x to the greatest x, and that'll get us the volume of the solid. If the thickness of our slice is a small change in y, we'll integrate from the smallest y to the greatest y. We usually see C to D for those. And this is called the disk method. So I'm going to show you with examples. I think you're going to love it. Oh, that's where I was going to write it. Oh, well. So I have all the steps on your sheet, but you can just turn the page over. We're going to go right to the examples. Okay. So for all these problems, you're going to be given the equations of functions that enclose some region. Because first you just have to draw the area of the region that's going to be revolved. So the first thing we have to do is graph y equals x minus x squared. What is that going to be when we graph it? Y equals x minus x squared. Is it a line? No. Quadratic, so the graph will be a parabola. Is it a happy parabola or a sad parabola? Can you tell me where this parabola, because I have to draw a sketch, where it would cross the x-axis? Tim, are you texting? Oh, that's a calculator. Never mind. That's what's behind the books. But we don't need the calculator, though. We just need to think about it. What values of x make y 0? 0. So there's a point on the parabola. What other value of x makes y 0? 1. Without even doing much work. We know these are the x-intercepts, and you already told me that this was a parabola that was concave down because the coefficient of x squared was negative. So we have a parabola that looks something like this. We just have to have a little. So one of the graphs is y equals x minus x squared, and the other one is y equals 0. What does that look like? Line. The x-axis, right? So, the first thing you have to see is the area that's enclosed by these graphs. Now I got to color it in. That's what I do. Let's go in highlighter. I don't know. Green? Okay. That's green. Oh, yeah, we'll do a bunch of them too. No, we've done more. Sorry. Now, so first thing you do is you figure out, all right, what's the enclosed region? Got it. That's the area we're going to be revolving. Now, what are we revolving about? In this case, it says the x-axis. So what you do to indicate that on your diagram here is you draw a curved arrow to indicate you're going to be revolving that about the x-axis. Now, if I took this region, now I can't draw this coming out of the page, but can you picture going around the x-axis and going back, what that solid would look like? Like what? Like a cheese? Is that what I heard? Like a cheese? Yeah, okay. Okay. All right. I guess. How? Well, here's what I do is, to illustrate the best I can, and I'm sorry if I offend any of the artists in the room. I just kind of, I know I can't draw it out here, but I just draw the other side. Oops. Oh, I'm sorry. That was really bad. Double better. Okay. Now, we want to draw in a slice, a representative slice. Now, whenever you slice these, you always go perpendicular to the axis of rotation. So each slice is going to look like a disc. And the way you can draw it, you don't have to draw it, it just makes it more fun, is you draw like an elongated circle from one side of the solid to the other. And here's where the artistic effect comes in. You give it a little thickness. You follow one of the sides down. And then it's like, oh yeah, I see it. You see the disc? Does it look 3D to you? Whoa, it's like popped right out, right? You don't see it? What if I like put little slash marks on the sides of it so you can... So there's just one disc, but you're going to have smaller disc here and larger. It's like a weird loaf of bread. And the way we're going to get is a slice. Yeah, if you took one rectangle, you spun it around, you're going to have a disc. Okay, if you started with one strip perpendicular to the axis, you spun that one rectangle around, it would be a disc like this. And the idea is that to get the volume of the whole solid, you sum up, you add up the slices, the volume of each slice of the bread. And then you get the volume of the whole loaf. Now, do you remember that each slice was pi r squared times thickness? Each slice had a volume of pi r squared times thickness. What you have to decide is the thickness going to be dx or dy? Yeah, a small change in x, dx. Now, I will tell you, for people who are worried, every time you revolve about the x-axis, the thickness will be dx. Whenever you revolve about the y-axis, the thickness will be dy. So, as long as you draw your slice perpendicular to the axis of rotation, you should see it. But so we said dx. Okay, so this is the volume of the whole solid. Now, the pi you can always pull out front. Pull that out front. It's a constant multiplier. But we're going to have to figure out what the radius is. So I'm just going to set up some parentheses with a little squared here. And we're also going to have to figure out the limits of integration. Well, let's do limits of integration first. That's fun. It's dx. So you want to add up the slices from the smallest x to the greatest x. What do you think, Amina? 0 to 1. Right? You want to add up these slices, these discs, from 0 to 1. Now, the radius, we got to figure out what to write in for the radius, is always the distance from the axis of rotation, right there, to the outside of the shaded region. Can you see that? It's always the distance from the axis of rotation to the outside of the shaded region. It's the radius. You don't want the diameter, you want the radius. Now, the radius is the length of a vertical segment. How do you get lengths of vertical segments? Think about our last unit. What did you do to figure out how far this is length right here? What top? Y top minus y bottom. Okay? What does y top equal? What does y on the parabola equal? Oops. Oh well. Sorry. Let me go here. Y top is y on the parabola, which equals x minus x squared. Minus y bottom, which is just 0. So I could write minus 0. Do you want me to write minus 0? I don't have to. I'll write it really small. Minus 0. Because you don't really need to write that. Okay. We've got the definite integral that's going to get us the volume of this solid of revolution. Now let's say we want to go get it, because we do. What would you do next? Square it. When you square a binomial, you could write it next to itself and multiply it out, but you should know the pattern. When you square a binomial, You square the first term, then you have twice the product of the two terms, and then the last term squared. Let's see what that's going to be. Okay, so first term squared, x squared, twice the product. The product of the terms and double it. Minus 2x cubed plus the last term squared plus x to the 4th. Now, if that threw you, what you do is on the side of your paper, you write x minus x squared times x minus x squared, and you FOIL it out. You do that so you buy it. You know, but it's a good pattern to know. Okay, we squared it out. Now what do we have to do? Integrate. We're going to find the antiderivative. I'm going to give myself a little room. What is the antiderivative of x squared minus 2x cubed plus x to the 4th? 1/3 x to the 3rd minus 1/2 x to the 4th plus 1/5 x to the 5th. Now this is a definite integral, so we are going to write the line here evaluated from 0 to 1. All right. So now we're going to leave the pi to the end. We're going to figure out the value of this, and then our answer will be whatever that number is, pi. Okay? So I'm going to have to plug in the upper, plug in the lower, and subtract to get the value of that definite integral. So we're going to plug in the 1 first, right? The upper limit. Okay, what's the first term going to be? 1/3, 1/3. Right, 1/3 times 1 cubed. Next term, minus 1/2 plus 1/5. And then we have to plug the lower limit into our antiderivative. No, it's all going to be 0. All right, well, I like to combine these fractions. We need a common denominator. What would that denominator be? 30? I like 30. All right, so they're all going to have a denominator of 30. 1/3. How many 30ths is 1/3? 10. How about 1/2? And 1/5 is 6. Let's count up, see how many 30ths we have there. 1/30th? I believe that. So let's see, we get an answer of pi times 1/30th, or just pi over 30. That would be the volume, that's the volume, of this solid of revolution. Got it? Ready to try another one? Yeah. So the first step is always figure out what region is enclosed. There's no good place to put this one. We want to find the volume of the solid generated by revolving the area in the first quadrant that's enclosed by y equals x squared and y equals 4. I'm going to revolve that region in the first quadrant about the y-axis. Y equals x squared, what's that graph? Parabola, so sketch that. And the line y equals 4, what kind of a line is that? Horizontal. Now the region that we're going to be revolving is in the first quadrant, so it's just here. Get out the monkeys. What are we going for? Lovely. Sorry, I didn't even ask your opinion. Okay. So we're going to go here. We needed something right here. Oh, a little too light. Oh. Now that region we're going to revolve about the y-axis. So we're going to indicate that we're going to revolve about the y-axis with a curved arrow. All right. What's that solid going to look like? What? Like a bowl that you can't put anything in because it's solid. So you go and it's like, oh, flat on top. Yeah. Okay, so it'd be like that. I always think of like a bullet. That's what I know. That's how I roll. But this is yeah, the whole thing would look like that. If we want to draw on one slice, since we're revolving about the y-axis, our slices would be horizontal. So if you want to draw it in and have some fun with it, you can draw in an elongated circle going left to right, and then you give it a little thickness by following one of the sides, and you can see an example, representative disc. And we're going to add them all up to get the volume of the whole solid. Not bad. When you start to write the formula, do you remember what you can pull out front? Pi. And we have the integral of r squared, but you have to tell me if it's dx or dy. dy. This time the thickness of our disk, of our slice, is a small change in y, infinitely small change in y. Nice. So you know we're going to have to figure out our limits of integration, and we'll have to figure out the radius and square it. Sometimes I set up the parentheses, would put the square there so I don't forget to square the radius. Let's talk limits of integration first. Well, we'll get to that in a minute, but to get the limits of integration, it's dy, so you want to add up from the smallest y to the greatest y of the shaded region. 0 to 4. Yeah, taking this, adding up the stack of these discs from 0 to 4. Okay, now I see what you're talking about. Now, as far as the radius goes, it's always the distance from the axis of rotation to the outside of your shaded region. The radius is the length of a horizontal segment. How do we get those? X right minus x left. So x on the parabola minus x on the y-axis, which you know what that is. The parabola, the equation is y equals x squared. So I have to know what x equals. Square root of y. And it's going to be the positive one because x is positive over here. Okay, so the radius is x on the parabola, which you just told me was the square root of y, minus 0, because x on the y-axis is just 0. So what would you do next? Okay. Yeah, the square and the square root. So we're going to square the radius, and that's just y. Okay, we square the radius. Now what? Integrate. Find that antiderivative. What is the antiderivative of y? Y squared over 2. I like it. And we have to evaluate that from 0 to 4. I never want to forget to take the antiderivative. But now, and we'll leave the pi out to the end, we'll just plug in the upper and plug in the lower and subtract, and we'll get our answer. Yes, sir. Yeah. 8 pi. You agree? Yeah, they agree. So So 8 pi cubic units, whatever they are, that's the volume of that solid revolution that we just had. Cool, eh? It's not bad. If you can just remember, it's just you integrate pi r squared dx per dy. That's the disk method. And for another one? There they do. They just yelled yes. Can't hear that. Ooh. And I'm trying to avoid going to the calculator whenever possible because you guys have so much graphing knowledge in you. We just got to pull it out. And you might look at that and say, ooh, I don't know what that is. You know, to graph that. What if you squared both sides? I think if you square both sides, it might help you to identify this graph. Say it again. It's a circle. See, if you move the x squared here, it'd be x squared plus y squared equals 9. And we don't have the whole circle because we have y equals the positive square root only. We have the top half of the circle where the y's are positive. So yeah, we're going to graph this. It's a semicircle. What is the radius of the semicircle? 3. So from -3 to 3. And we're only going to see half the circle because we're only looking at the positive y value. Y is the positive square root. Oh, I forgot to add in this one. I have to add it now. The area enclosed by the semicircle and y equals 0. Because I need to close it. So we've got to identify the region we'll be revolving. I'll let you guys have input this time. What do you think? Orange, we haven't done an orange. Is that orange highlighted? Or do you like that one? This one? It could be really scary. I don't know. So, that put me in a really bad mood. Well, next time maybe if we get to another one, we'll do magenta. I know this is a sad orange though. Well, I guess it's alright. It's kind of a brownish orange. What are we revolving this about? Oh, the x-axis. All right, x-axis. Just read that. So what is this solid going to look like when we take this semicircle and revolve it about the x-axis? A sphere. Do you see it's going to be a sphere? Isn't that fun to say? Sphere. All right. We're going to find the volume of a sphere. Awesome. Yeah, I'll draw it. I like to draw on the slices. And again, you don't have to do this. I like to draw the other side. And your slices always should be perpendicular to the axis of rotation. And draw one like this. Ooh, that was a little bad. It's the orange, it threw me. So volume equals, tell me what to rate to start this whole process off. Pi, I like that. Okay, the antiderivative of pi r squared dx. It's talking about the x-axis. That's going to be dx, but it's nice to see it. Love it. So we know we have to, for the disk method, we have to figure out the limits of integration, and we also have to figure out the radius. We'll do limits of integration first. -3 to 3. If you were thinking 0 to 3, you were looking at the y instead of the x's. It's dx, so you have to look at, go from the smallest x to the greatest x. So it is -3 to 3. What is going to go good on that? I know I can't do red. I guess I'll do the blue. For the radius, it's always the distance from the axis of rotation to the outside of the shaded region. Yeah, it's the radius I labeled. The radius is the length of a vertical segment. So how do we find that? Y top minus y bottom, right? So what should I write in for the radius? Rad 9 minus x squared minus 0. All right, we don't even have to. What would you do next? What do we do? What do we do? Square the radius. Exactly. That's not too bad. Squaring a square root. That's nothing but fun. So we squared the radius. What's the time to do? Anti-differentiate. That's the word. That's the word. So what would the antiderivative of 9 minus x squared be? 9x, 1/3 x cubed, or x cubed over 3. And we have to evaluate this from -3 to 3. We'll leave the pi out of this. So we have to plug in the upper, the lower, and subtract. Plug in the 3, the upper limit first, and we do it using the fundamental theorem of calculus. 9 times 3. 27 minus 3 cubed over 3. 3 cubed 27 over 3 would be 9. 9. Then we'll do the same thing with the -3. 9 times -3, -27, minus -3 cubed over 3, plus 9. Good. So we get pi times 18 minus -27 plus 9 minus -18. 36 pi. That is the volume of this solid, this sphere. Remember, it was a sphere? And we could have just used the old volume formula for a sphere. Remember the volume of a sphere? What the formula was? It had a 4/3 in it. 4/3 pi r. If it's volume, it's got to be cubed, right? Now, I wonder if that would have worked. The radius of that sphere would have been 3, right? If I put in a 3 for the radius, I have 4/3 pi times 3 cubed. Well, one of the 3's would cancel. That would be squared. Oh, it's 36 pi. But using a formula is boring, right? When you can use integration to get the volume, right? Who ever wants to use formulas again? So yeah, we could have got 36 pi with a formula, but this was more fun. So you have 2 problems to do for homework. Yes? Oh, so when you have the line, and then the x, so you have this triangle, and we're spinning it about the y-axis. Bless you. When you draw this thing, what is it going to look like when you go around? Can you picture taking this? I know it's not colored in. A cone, yeah. Each slice going about the y-axis can go this way. The radius is always the distance from the axis of rotation to the outside. So you're going to have to do x on the line minus x here, which is 0. So you're going to have to solve for x on the line, because the radius is x right minus x left. You've got to look at the equation of the line here and solve for x. And that'll be your radius. Nice, kids.